Extremely sorry for the without outro. I had to end up the previous lecture, so it's just a continuation of the previous part. So there we will be covering the part where we will be going through the resonance condition and Bohr's frequency rule. So after we have covered that what were the three interactive way through which our photons react, we have studied about absorption, emission and scattering part, and now we will decide that if it will absorb and emit when the energy level matches the gap between two molecular energy level. So basically you could see the formula over here that E2 minus E1 is the gap of energy, and through this we can understand that energy is equals to h nu, or hc by lambda is equals to hc into nu bar. So overall this is the equation, but you could see that mathematically it would be repeating again and again. So after this part, if the photon is of resonance, it passes right through without any kind of interacting. This is exactly why spectra show distinct lines or bands instead of continuous rainbow. I hope it is clear. Okay, so now coming to the most important part, that is our selection rules. So the selection rules actually revolves around two factors. One is allowed, another one is forbidden transition. Okay, even when the resonance condition is satisfied, a transition occurs only if the corresponding selection rule is obeyed. So selection rule comes from the requirement that the transition dipole moment integral be non-zero. So what do I mean to say this about? This means that even if a photon has the perfect energy, a transition will only happen if only it obeys this rule. So what does this rule say? Where do they come from actually? They are calculated from the transition dipole moment integral. Okay, that is denoted by what? Our mu 1 to 2. Okay, through this we will be denoting it. The transition probability is directly proportional to the square of this integral. So you can see this is the thing, this is our probability, and this is what? This is our transition dipole moment integral. Fine. So this is the formula, and through which you can say that how we can write the whole overall transition dipole moment integral. Fine, remember these things, very important for your equation part. If they're asking you to give definition, try to add these equations, it will give you more age and number as well. Without further delay, you can see that we have two things, two general selection rule. One is our gross selection rule, another one is our specific selection rule. In the gross selection rule, the molecule must possess a property. What is that property? That is permanent or oscillating dipole capable of interacting with the radiation. This is our gross selection rule. And what do you think that this gross selection rule actually means for us? This means that generally when the property of a molecule has some change, there would be some permanent or oscillating dipole in it. And the specific selection rule says that the change in quantum number must obey definite values. For example, nu is equals to plus minus 1, and change in energy should be in plus minus 1, and length is also plus minus 1. Fine, through this they will change, otherwise there will be no such thing that is in like not completely discrete like 0.5 or something, not like that, because it's a quantum number. You need a complete number for it for that changes. I hope this part is also clear. Now coming to the part of selection rule across the spectroscopies. Okay, I think this part is very important probably because you could see different type of spectroscopy are written over here. The gross rule must have, and the specific rule present over here. So for the rotational, or you can say microwave, permanent electric dipole moment, okay, is our gross rule must have, and our del J is equals to plus minus 1. And in vibration must change dipole moment. Okay, and nu should be plus minus, that is our harmonics. There will be a change. Okay, plus minus 1, plus minus 2. Okay, by this way, this is the vibrational changes. We will be covering each and every spectroscopy one by one. This is just the introductory part, so let's cover it up ASAP so that we can go to the main parts and fire you the questions from where question repeats again and again. I have tried to add problems questions over here so that you can get an overview how to write your answers and attempt it. Okay, then we have our Raman spectroscopy, where vibration must change polarizability. Okay, and here you can see that your del V is plus minus 1 and del J is plus minus 2. Okay, in electronic, that is our UV visible spectroscopy, allowed orbital symmetry transition. Okay, where del S is equals to 0, that means spin number is equals to 0, and del L is equals to plus minus 1. Okay, and finally our NMR spectroscopy, where magnetic spin is not equals to 0 in field B naught. Okay, and del M1 is equals to plus minus 1. Here we consider the mass part. Fine. And ESR spectroscopy, there is unpaired electron where S is not equals to 0. Fine. Here also del MS is equals to plus minus 1. So overall you could see that the gross rule and specific rule, through this way we can say you about the complete selection rule of spectroscopy. Listen, you don't have to memorize everything, just go through this lecture once and then you will understand the overview of it. And the question that can come to your exam, that is, for example, while N2 shows no why N2 shows no IR but shows Raman spectroscopy. Okay, see, problem is that predict whether N2 molecule shows IR absorption or Raman scattering, and the solution is very simple to it. Okay, because N2 is a symmetric homonuclear diatomic molecule. Its dipole moment remains exactly 0 throughout its stretching vibration. Therefore, it is IR inactive. I hope this is clear. Okay, but for Raman, the vibration must change the polarizability of the electron cloud. Then the NN bond stretch does change polarizability. So this is Raman active. Okay, actually the thing is what you need to understand, where IR is inactive and where Raman is active. So the thing is what the dipole moment is 0 throughout the stretching vibration. That's why this is a IR inactive, because we have seen that if it should be IR active, there must be some change in dipole moment. Okay, but there is no change. But in case of Raman active, there is vibration change that due to the polarizability. So this is very clear to you, I hope. And if I have said something wrong in between, so I'm sorry for that, because I think I have some like twist of tongue, so please excuse me. The things is very simple, because it doesn't have any stretching vibration and dipole moment change. So this is IR inactive N2, and due to vibration must change due to the polarizability of the electron cloud present in NN bond, the stretch does change polarizability. Due to this is Raman active. I think this is very simple and clear. So now, mutual exclusion principle, I think one of the most important part of this spectroscopy chapter. Okay, this brings us to a beautiful rule that for any molecule that has a center of symmetry like CO2 or N2, a vibration that is IR active must be Raman inactive, or you can say vice versa. Like the previous questions shows you that in this question you have seen that N2 is your, I am writing over here that N2 is your what? Raman active. Okay, but IR inactive. Fine. So you can say through here that your Raman inactive and IR active, they are working as vice versa. Okay, So this is a very powerful structural fingerprint and a common question. Okay, now your last part probably of this, your population and line width part. Okay, let's wrap up this part 1 with this. So the intensity of absorption line depends on how many molecules occupy the lower level at thermal equilibrium. The Boltzmann distribution governs this population. So what is your Boltzmann ratio? So come to this point. What is your Boltzmann ratio? See, you could see the formula very easily. N2 by N1 is equals to G2 by G1 exponent of minus del E by Kb into T, where G1 G2 are degeneracies. Okay, Kb is your Boltzmann's constant, that is 1.381 into 10 to the power minus 23 joule Kelvin inverse. Okay, please remember the units, I beg you guys, because else you will repent. The simple thing is that. Okay, now what do you mean to say that in NMR the energy gap, that is your del is incredibly small. Okay, that means the ground and the excited population are almost at equal stage, because the net population difference is so small that NMR is inherently a low sensitivity technique. Another popular example, you can say that. Okay, so this implication should be kept in mind thoroughly. Now our resolution and line width part, that is our the Heisenberg limit, the Heisenberg uncertainty limit. What was that? Spectral lines are not infinitely short, they have natural width set by lifetime of the excited state through Heisenberg's uncertainty principle. Okay, so here you can see that del E multiplied by del T is greater than, or you can say greater than equals to your Planck's constant by 2. And I think this is one of the most important equation, and I think you have already read about it in your quantum part. Okay, and these are the everything you can say. And other boarding sources was Doppler broadening, collision broadening. You could see this part, or it's just for a note stuff, you can just ignore this part. I would probably suggest read the notes that I'm providing you, and I think that would be more than enough. Okay, so from exam point of view, I would just say that some more things, that if excited state has very short lifetime, that is our tau. Okay, its spectral line will be broad. If it has long lifetime, the line will be sharp. Other real world factors like molecular collision and gas phase Doppler shifts broadens the line further. Okay, this is the simple way to figure it out. If you want, I can write it over here for you. Okay, I'm writing it. What do I mean to say, so that through notes you don't have to get fear. Okay, I mean to say that simply I'm writing that if excited state is there, state has a very short lifespan, then it is what? Then it has a broad line. Okay, but if it has long lifespan, sharp line, and these factors, this outboarding factors, okay, definitely going to affect you. Okay, this ongoing factors definitely going to affect your broadening. Okay, when you will see that this real life effects and the line gets broader, that's the simple thing I could say you. So let's bind up over here, let's not drag it, let's meet you on the next part.